Welcome back to Applied AI Engineer. For 15 episodes, Atlas has lived inside a Python script, brilliant, but trapped on your laptop. Today we set it free. We wrap Atlas in a real web service, a FastAPI app that streams answers token by token over server-sent events, reads its secrets from the environment, protects itself with rate limiting, ships inside a Docker image, exposes a health check the orchestrator can probe, and serves a tiny chat page so a human can actually talk to it. By the end you'll have a deployable API and a Dockerfile, the moment Atlas stops being a demo and becomes a product. Last episode we made Atlas observable, we tracked tokens and cost on every call, measured P50 and P95 latency, and built a router that sends easy work to Haiku and hard work to Opus. That gave us a model that's measured and cost-aware. Today we cross the last line before production. We put that model behind a network boundary. A streaming endpoint, configuration from the environment, a rate limiter so one caller can't sync the service, a Docker image so it runs identically everywhere, and a health check so your platform knows it's alive. Deployment is more than getting code onto a server. It's about contracts and guarantees. You expose a stable HTTP interface so clients depend on the endpoint, not on your internal functions. You read configuration and secrets from the environment, so the same image runs in dev, staging, and prod with only the environment changing. You add the resilience a public service needs, rate limits, timeouts, health probes. And you package everything into one reproducible container. Get these 4 right and Atlas behaves the same on your laptop and in the cloud. Here's the whole shape. On the left, a browser or any HTTP client sends a prompt to our FastAPI service with a post to /chat. Inside the service, the request first passes a rate limiter, then we read the prompt and call the Cloud API with the key pulled from the environment. As tokens stream back from the model, we relay each one straight to the client as a server-sent event. Off to the side sits a cheap /health endpoint that the orchestrator probes without ever touching the model. One process, 4 responsibilities: validate, limit, call, and stream. Before a single endpoint, we settle configuration. The cardinal rule of deployment is that config lives in the environment, never in the source. Let's build one small settings object that reads everything once at startup. This is the 12-factor pattern in miniature. A frozen data class holds every tunable, the model, the token cap, the rate limit, each with a sensible default that an environment variable can override. The one true secret, the Anthropic key, is read here, but we never print it or return it in a response. We build the settings object once at import time and share it across the app. Change the model in production. Set Atlas_model and restart, no code change, no rebuild. Here's the heart of the streaming service, one async generator that yields the reply token by token. If a real key is present, we open Anthropic's async streaming client, the same call from episode 1, now asynchronous, and yield each text delta as it arrives. If there's no key, we fall back to a clearly marked stub that streams a canned reply with the same shape. The crucial design choice, the endpoint above this never knows or cares which path ran. The streaming contract is identical, so we can develop and demo offline and flip to live Claude by setting one variable. Now the endpoint itself. We want answers to stream to the browser the instant they're generated, the UX we proved back in episode 1. The cleanest transport for that is server-sent events. Server-sent events is beautifully simple. The client opens one HTTP connection and the server holds it open, writing small text frames as the model produces tokens. Each frame is an event line, a data line, and a blank line to close it. The browser fires a callback on every frame, so the answer visibly grows. When we are finished, we send a done event with a done marker. It's lighter than WebSockets and exactly the right shape for one-way token streaming. The SysStarlet library turns an async generator into this wire format for us. We just yield a dict per frame. We create the FastAPI app and a rate limiter sized from settings, then define the health check first. This is the endpoint your orchestrator, Kubernetes, ECS, a load balancer, hits every few seconds to decide whether the instance is alive and ready for traffic. The golden rule: a health check must be cheap and must never call the language model. If it did, every probe would cost tokens and a slow model would look like a dead server. We return plain status and which model is configured, and note we expose whether a live key is set, not the key itself. Here's the streaming route, and it reads like a checklist. Pydantic validates the incoming JSO, a missing prompt is rejected with a clean 422 before any work happens. We pull the caller's IP and ask the rate limiter if they're within budget. If not, we return a 429 immediately. Then the real work: an inner async generator pulls tokens from stream reply and yields one SSE frame per token, finishing with a done frame. We hand that generator to event source response, and SysStarlet streams it to the client. The whole endpoint is a dozen lines, and every one earns its place. A public endpoint without a rate limit is a liability. One buggy client or one bad actor can hammer your model and run up an enormous bill in minutes. Let's add a small, honest limiter. This is a sliding window limiter per client key. For each caller, we keep a dequeue of recent request timestamps. On every call, we evict anything older than 60 seconds, then check. If the caller already has too many hits in the window, we deny, otherwise we record this hit and allow it. It's a dozen lines and perfectly adequate for one process. In a real fleet, you'd back this with Redis, so the limit is shared across all your replicas, but notice the interface: a single allow method wouldn't change at all. That's the scene you'd swap behind. Talk is cheap. Let's run the service for real and watch actual bytes come back. We'll drive it with FastAPI's test client, which exercises the genuine app routing, validation, streaming, and all. Test client spins up the real USGI app in process and lets us make real HTTP calls against it. No mocking, no separate server to manage. We first hit /health and print the JSO. Then we open a streaming post to /chat and iterate the response line by line, printing the raw server sent event frames exactly as they cross the wire. This is the honest test. If streaming is broken, we'll see it here. Let's run it and read the true output. There's our health probe, a 200 status, and a small JSO body reporting status OK, the configured model, and that no live key is set, so we're on the stub path. This is exactly what a load balancer wants: a fast, cheap yes or no that never touches the model. The live model flag is a nice operational touch. At a glance, you can tell whether this instance is wired to real Claude or running the offline stub, without ever exposing the secret. And here is real streaming. The content type is text/event stream. That's the browser's signal to treat this as a live feed. Then frame after frame, each one an event line and a data line carrying a single token, just as the diagram promised. The frames arrive one at a time, not in a single blob, which is the whole point. Finally, a done event with the done marker tells the client the stream is complete. This is genuine output from the running app, not a mock. If we concatenate the data fields from every token frame, we get the complete reply, the stub scanned message, here, but with a live key. This is real Claude text streaming through the very same code path. The stub even echoes the prompt back, proving the request body was passed and routed correctly. Flip on a key and this becomes a genuine model answer with zero changes to the endpoint. That swappable scene is what lets you build the whole service offline and go live with one variable. And the limiter works. After filling the per minute window for this client, the very next request comes straight back with a 429 and a rate limited body, no model call, no cost incurred. This is the difference between a toy and a service. The toy happily lets one caller drain your budget. The service says no, cheaply and immediately. A real client would read that status and back off, exactly as our resilient caller did back in episode 1. Once the server is up under Unicorn, anyone can hit it with plain curl, no SDK required. The -n flag is the important one. It disables curl's output buffering so you watch the SSE frames stream into your terminal in real time, exactly as the browser sees them. This is the proof that Atlas is now a real networked service. Any language, any client, any platform that speaks HTTP can talk to it. That's what crossing the network boundary buys you. The code runs on your machine. To run identically anywhere, we package it into a Docker image. The trick is ordering the layers so rebuilds stay fast. A Docker image is a stack of cached layers, built bottom to top. The base Python image at the bottom almost never changes. Above it are non-root user and working directory. Then the expensive layer, installing dependencies. Then, deliberately last, copying our application code. Why this order? Docker catches each layer and only rebuilds from the first one that changed. Because code changes far more often than dependencies, putting code last means a one-line edit to app.py rebuilds only the top 2 layers seconds, not the minutes a fresh pip install would cost. Read this top to bottom and every line is a deployment lesson. We start from a slim Python base and immediately create a non-root user because a container should never run as root. We copy requirements first and install them, that's the cached layer, then copy the code. We drop privileges with user Atlas, document the port, and add a container-level health check that curls our own /health endpoint, so Docker itself can tell when the app is unhealthy. Finally, we launch Unicorn bound to all interfaces. Notice the key is nowhere in here, it's injected at runtime. 2 commands ship it. Build tags the image, run starts it, maps port 8000, and injects the API key as an environment variable. This is the payoff of reading config from the environment. The image is identical everywhere and contains no secrets, so it's safe to push to a registry. The same artifact you tested locally runs in CI and in production, only the injected environment differs. That reproducibility is the entire reason containers won. An API is enough for machines, but a human wants something to type into. Let's serve a minimal chat page that reads the same SSE stream, so Atlas finally has a face. This is the browser side, and it mirrors the server exactly. We post the prompt with fetch, then read the response body as a stream. As bytes arrive, we buffer them and split on the blank line that separates SSE frames. appending each token's data to the page the instant it lands. The done event ends the loop. The effect is the live, growing answer every chat app gives you, and we built it in 20 lines of plain JavaScript, no framework. FastAPI serves this file from a static folder at the route, so opening the server in a browser just works. Before you call anything shipped, run this checklist. Secrets come from the environment or a managed secret store, never the image or Git. Every public endpoint has a rate limit, and every model call a timeout. A cheap health endpoint reports liveness, and you keep the structured logging and cost tracking we built last episode running in production. The container runs as a non-root user with pinned dependency versions, and the exact same image flows from your laptop through CI to production. None of this is glamorous, and all of it is what separates a weekend demo from a service people can rely on. Let's recap. Atlas is no longer a script, it's a streaming web service. It pushes answers token by token over server-sent events, reads its config and secrets from the environment, protects itself with a per-client rate limiter, answers a cheap health probe, and ships inside a layered Docker image with a small chat UI on top. You have a deployable API and a Dockerfile. Atlas is officially shippable. That closes the production module evaluation, guardrails, observability, and now deployment. Next episode begins the two-part capstone, Capstone 1, where we assemble everything we've built: ingestion, the production vector database, the LangGraph agent, tools, and memory into the complete agentic RAG Atlas, answering a real multi-step question end-to-end. We've gathered all the parts. Now we build the whole thing. See you there.